The only two base logarithms that you have on your calculator are log base 10 and log base e. So far, when we have had to evaluate logarithmic expressions other than base e or base 10, they have been made up so that we could do it in our heads, like what's log base 2 of 64? Well, since 64 is a power of 2, that's not hard to figure out. But if you ask me for log base 2 of 20, I could tell you what it's close to. I could tell you what two whole numbers it's between. What would log base 2 of 20 have to be between? 4 and 5, because 2 to the 4th is 16, that's too small. 2 to the 5th is 32, that's too big. But somewhere between 4 and 5 is as accurate an answer as I could give you until I learn the change of base theorem. The change of base theorem allows me to change other base logarithms to bases that I have buttons for on my calculator, either log base 10 or log base e. The change of base theorem says log base a of v equals, if you change it to log base 10, it'll be log base 10 of v over log base 10 of u, or you can change it to natural log of v over natural log of u. Yeah, that's log base u of v. Oh, okay. All right. No problem. Actually, the change of base theorem says you can change log base u of v to anything. You could change it to log base 7 if you wanted to. That usually wouldn't help you because you don't have a log base 7 button on your calculator either. And that's why we just change it to either log base 10 or natural log. Does the fact that log of v over log of u is the same thing as natural log of v over natural log of u, does that mean that log and natural log are just the same thing? No, they're not just the same thing, but the ratio of those two logarithms is the same. Let's see what these two problems on page 348 are. Number 6 and number 8. Oh, that's so easy. Hey, I didn't realize that I had just made up number 6, log base 2 of 20. That's kind of funny, because I did not look at the book before I said that. We know that it's between 4 and 5, because 2 to the 4th is 16, and that's too small. 2 to the 5th is 32, and that's too big. So all I know is it's 4 point something something. But with the change of base theorem, I can change it to an expression I can enter on my calculator and get a much more accurate decimal representation. So what would that be if I changed it to natural log? Yep. And if you have trouble remembering which one goes in the numerator and which one goes in the denominator, the 20 is over the 2 on the left-hand side. The 20 is over the 2 on the right-hand side. That'll help you remember which one goes in the numerator, which goes in the denominator. To the nearest 4 decimal places, I think that's 4.3219. The book doesn't specify how many decimal places we should keep, so you use your best judgment and I'd count it right. Do you get the same answer if you use the log base 10 button on your calculator? Try it and see. Log base 10 of 20 over log base 10 of 2. Yeah. And that does not mean that log and natural log are just the same thing and interchangeable. It's the ratio that's the same, the ratio of those two logs. All right. Number 8 before you grab your calculator, I want to ask you something. Log base 6 of a half. What do we know has to be true about an exponent of 6 that gives me a half? It has to be negative. If I punch it on my calculator and don't get a negative, I've punched something wrong or my batteries are dead. Change that to, let's say, natural log. And it's easier to put that a half in as a decimal. Natural log of 0.5 divided by natural log of 6. I get that to be negative 0.3869. So the change of base theorem can definitely come in handy sometimes. Everything else that you have to do in the homework is solving equations. And I love the handy-dandy handout that breaks all of these equations into one of two types. Either they're exponential equations or they're logarithmic equations. College algebra, one time I had somebody say, how do you know which ones are logarithmic? They have logs in them. The ones that don't have logs in them are exponential. But not only can we break it into those two categories, under each two categories we can say there are two cases of exponential equations and there are two cases of logarithmic equations. I believe we've solved all the types except for case 2 of exponential. We've already done case 1 of exponential. If you can write both sides having the same base, then just take off the bases and set the exponents equal to each other. So that's always the first thing you need to ask yourself when you see an exponential equation. Say, can I write both sides having the same base? Because that's definitely the easiest way. But if the answer to that is no, then how are we going to get those exponents out of the air if we can't write both sides having the same base? Log or natural log of both sides. And it doesn't matter which one you use, as long as whatever you do on the left, you do the same thing on the right. When you cannot write both sides having the same base, then get the exponential expression on a side by itself on one side of the equation by adding, subtracting, multiplying, or dividing. 2, take the log or the natural log of both sides. 3, bring the exponent out front using property C, which is the one that says we can bring the exponent out front. And then number 4, solve for the variable. Very important in boldface type, do not evaluate any part of the expression before the variable is by itself. That means don't pick up your calculator in step 2 and punch natural log of 8 and then round that to something and finish the problem. Once you've made a rounding, once you've rounded in some step of a problem, you've introduced an error into the problem. It may be a small error, it may only be an error in the 1,000th place, but every step after that, if you multiply that error in the 1,000th place by 10, then all of a sudden you have an error in the 100th place. So if you round at the beginning, then your rounding error gets larger and larger throughout the problem. It still may not be significant to anyone working at McDonald's, but it's significant to someone working at NASA. And I know that's where all of you are headed. So don't pick up your calculator until you have the variable by itself. If not because you're headed for NASA someday, then because if you get the variable by itself before you punch it on the calculator and you have that expression right, I'll give you most credit for it on the test. But if you start rounding up in step 2 and then you don't have the exactly right answer, it's just wrong. Get that variable by itself so I can see what you punched on your calculator and give you credit for that, even if you have the answer off a little bit. All right, I've done one beautiful example for you, typed up one beautiful example, and then we'll work some others. 500 times 1 plus 0.05 to the p over 4 equals 200. That's an exponential expression. I can't really tell whether or not I can write both sides having the same base until I get the exponential expression by itself. So the first thing I do is divide both sides by 500. Since 200 divided by 500 is a terminating decimal, I'll write it as a decimal. But if that were 200 over 300, I would not write it as a decimal. I'd reduce it to 2/3, but I'd leave it a fraction. All right? At that point, I can see I can't write both sides having the same base. So I'm going to have to take either the log or the natural log of both sides. I chose to take the natural log of both sides in the third line. And in the fourth line, that allowed me to bring the exponent out front. Then finally, to get the p by itself, actually I got the p over 4 by itself by dividing both sides by natural log of 1.05, and then multiplied both sides by 4, and this is the exact answer. 4 natural log of 0.4 divided by natural log of 1.05. That's the exact answer, and that's about 3 points on the test. To get the other 2 points, you have to know how to punch it correctly on the calculator and round. On the test, I probably specified 3 decimal places. If I didn't specify 3 decimal places, then use your best judgment and I'll count it right, but 3 decimal places is good enough.
So
Now, give me 20 decimals.
So if we punch it in and we get that wrong, if we punch it in wrong, do we get it all wrong?
No, if you get the p by itself before you pick up the calculator and this is what you have, you have 3 points out of 5, even if you punch it wrong on the calculator.
Do you count off if we punch it wrong?
Yeah, you got to have the right answer. This is their last 2 points right there.
Oh, okay.
All right. Since that is the only kind of problem that we have not yet done, I'm going to go ahead and mention these 2 cases of logarithmic equations, and then however much time we have left, we'll find some more like this. The 2 cases of logarithmic equations were in last night's homework. Either you can write both sides as single logarithms having the same base, in which you do that and then remove the logarithms, set the arguments equal to each other. Or you can't write both sides having the same base, so you get all your logs on one side and a constant on the other. Put all your logs together as a single logarithmic expression and then change it to exponential form. And don't forget, whenever you solve a logarithmic equation, you have to check and make sure that your proposed solution doesn't make the argument 0 or negative. The example I typed there is very much like one you could have done in last night's homework. I put that back together as a single logarithmic expression. Since that was the common log, log base 10, when I changed it to exponential form, the base was 10. I had a quadratic equation, so I got it in standard form, prayed that it would factor, and it did, and got to propose solutions. Now, do you automatically say, oh, W can't be negative? No, sometimes W can be negative. The argument can't be negative. And since W is the argument of this first logarithm, then I can't use negative 2/3. So the answer is only number 5, or the number 5. All right. Let's find a couple other exponential equations to solve. 11 through 24 say find the exact solution using common logarithms. I don't care if you use common logarithms, you can use natural logarithms, either one, and a 2 decimal place approximation of each solution when appropriate. I'm not sure when it would be inappropriate, but okay. Number 12. Is this an exponential or a logarithmic equation? Exponential. Can we write both sides having the same base? I don't think so. It would not be easy. So what do? Take the log or the natural log of both sides. The book says common log. Natural log's fine. And what does that allow us to do? Bring the exponents out front. I've just made a college algebra mistake that I know nobody in pre-calculus would make. What is it? Without parentheses, the 2x wasn't part of the exponent. I'd only put the 3 back as the exponent. So make sure you use parentheses where necessary. That was actually the easy part. Now we have to figure out how to solve for x. Any idea? That would be legal. I'm not certain that that would be helpful. Let me show you what to compare that to and convince you that the rules aren't changing just because the problem's uglier now. What that is just like would be the much simpler looking equation. 4 times 2x plus 3 equals 5 times x minus 2. I am not saying throw away the logs. I'm saying however you solve this equation, you solve this equation the same way. 4 is a constant, 5 is a constant, natural log of 4 is a constant. It's 1 point something something. I can distribute it just like I could distribute the 4. So that's the first thing I need to do, distribute. That's what I would do over here on this simpler problem. I would say now I have to get all the terms with an x on one side and all the terms without an x on the other. So that's exactly what I do here. And I try to see, it doesn't matter if you get your logs on the left or to the right, I try to get them on the side that would leave me the least negatives in the problem. Would I have less negatives in the problem if I moved the logs to the left or to the right? I think to the right I would only have one subtraction. I could add that 2 natural log of 5 to both sides. The reason I try to keep as many logs as possible positive is because logs that are added I put back together as multiplication. Logs that are subtracted I have to put back together as division. So I want to keep as many logs possible as positive as possible. So I would choose to move my x's to the right. Then how do we solve for x if it's part of 2 terms that aren't like terms and I can't combine them? You can factor out an x. In that same step, I'm looking forward to punching this on the calculator and thinking this would be easier to punch as natural log of 4 cubed or just natural log of 64. And the second term would be easier to punch as natural log of what? 5 squared, or go ahead and say 25. Is everyone okay with that left-hand side? On the right-hand side, factor out an x. And then, again, looking forward to punching this on the calculator, what's the more simple way I could write that left-hand side? Natural log of 64 times 25. And what would this stuff be inside parentheses if I wrote it as a single logarithm? 5 over 16. Good. Any questions about that? Just trying to make it as easy as possible to punch on the calculator. X would be the natural log of, what's 64 times 25? 800, 8,000, something. Well, I missed that one, didn't I? Natural log of 1600 over the natural log of 5/16. That's the exact answer, and that's 3 points on the test right there. But to get the other 3 points, you're going to have to actually punch that correctly on the calculator. And my book says that's negative 6.34. Terry, do you have an 83, 84, or 86? 84, then as soon as you hit natural log, your calculator opens this parenthesis for you. Just type 1600, close parentheses, and then divided by natural log. The calculator will open this parenthesis for you. 5 divided by 16, close that parenthesis, and enter. Did it that time? Yeah. Okay. There are things that I prefer about the 86 and things that I prefer about the 83 and 4. One of the things I like better about the 86 is it doesn't open parentheses for me. When the calculator automatically opens a parentheses that turns out to be unnecessary, like this natural log of 1600, you don't really have to have that in parentheses. But because the calculator opens it and you don't really need it, I forget to close it sometimes, and you get the wrong answer. Number 8. If you can find it, I can look at it with you after class and help you punch it. Okay. All right? All right, let's do one more. Number 24 looks interesting. Let me see if anything before that looks interesting.
Can I ask you a question?
Yes, ma'am. Uh-huh.
In this step where you got natural log of 64 plus natural log of 25, that line, what did you say we did to just combine?
How do you put the sum of two logs back together?
Okay, so we're putting the logs together. I'm just writing this down.
Yeah, that's fine. Put the sum of two logs back together as a log of a product. And Emily, you wouldn't actually have to do that if you had natural log of 64 plus natural log of 25 in the numerator and you punched that correctly on the calculator, that would be fine. I just thought it would be easier to put on the calculator if I put that back together as a single log, because it takes less parentheses to punch it. Number 14 is just like 12. Number 16 is about the same. Number 18 you could have done in last night's homework. 20 you could have done in last night's homework. 22 and 24 we better do 22. You didn't do anything like that last night. And your homework stops at 21, so this is good. Now, honestly, I'm not sure if I would have known how to begin that if I hadn't looked in the solutions manual the first time I did it. I've been doing it for 12, 15 years now, same problem. But I think I would have been stumped the very first time I looked at it until I looked in the solutions manual and went, oh, that makes sense. So I wouldn't necessarily expect you to be able to do 21 unless I showed you one just like it. Once I show you one just like it, I think you can do 21. The whole trick here is writing that 3 to the negative x in the denominator as 3 to the x and then clearing out the fractions. After you clear out the fractions, it gets much better. So let's see. 3 over 3 to the x plus 9 over 3 to the x equals 28. And then how would you clear out the fractions? Multiply all three terms by 3 to the x. On that right-hand side, can I go ahead and say 28 times 3 to the x is 64 to the x? No, that would be highly illegal. Highly, highly illegal. I can, in this first term on the left, say that 3 to the x times 3 to the x is what?
22x. No. Is it 9? I don't know.
When you multiply two expressions with the same base, you don't do anything to the bases, you just add the exponents, 3 to the 2x. So, well, keep up with that other 3, but you have 3 times 3 to the 2x. Plus 9 equals 28 times 3 to the x. Still looks pretty crazy. Just about anything other than a linear equation, we get it set equal to 0 and then try to figure out something. So I would subtract the 28 times 3 to the x. And I'm going to put it in the middle as the middle term. When I do, it's starting to look vaguely like something I do know how to do. Yes, this is like a quadratic equation because that 3 to the 2x, if I needed to, I could write it as 3 to the x squared that looks just like a quadratic equation, except for instead of having a plain old x, I have a 3 to the x. And Mr. Luke, on a similar problem, I think you've suggested before that we just use substitution. Just let 3 to the x be u for ugly and see if we could solve it then. Any questions so far? Now that I've let 3 to the x just be u for ugly, it is a quadratic equation. It's even a quadratic equation that I can factor. So either ugly equals 1/3 or ugly equals 9. Is that my two solutions, 1/3 and 9? That's just what ugly is, and I'm not solving for ugly, I'm solving for x. So how do I find out what x is? Put 3 to the x back in the place of ugly. What power of 3 gives you 1/3? What power of 3 gives you 9? That's your solutions.
And do we have to recheck this? We don't have to check it because there's no log, right?
Right.
Okay.
You can check it. It's good to check it, but you don't have to check it because neither one of those should be an extraneous solution. All right. The homework is at the bottom of the handout, 4.6, numbers 5, 7, 11 through 21, and 2 word problems. They're 2 word problems, just like other word problems that you've done. And most importantly, print that practice test and not start working on it, finish it by next Wednesday so that you can come in and ask me good questions. What I think you'll discover when you print it and look at it is these aren't as hard as some of the problems in the homework. And that's on purpose. I always make a test that way. I'm never going to put the hardest problems in the homework on the test. So y'all work hard, get that done, and ask me good questions Wednesday. And have a little bit of fun on fall break.
5 minutes.
At least 5 minutes worth of fun.